All right, let's get into it. We're about to pull back the curtain on the invisible architecture that honestly runs our entire modern world. Let's dive in.
I mean, really think about that. You've got a holiday rush or some huge flash sale going on, and thousands, maybe millions, of people are trying to grab the same handful of seats at the exact same second. How does the whole system not just completely crash, or double book seats, or even worse, just lose your money? Well, the answer lies in a set of brilliant and very, very rigid rules.
Before we had these super sophisticated systems, managing information was, well, it was a total nightmare. Just imagine every single department in a company keeping its own separate Excel spreadsheet. It sounds simple enough at first, right? But when you try to scale that up, you run into some massive, massive problems. And this lays out the core issues perfectly. When you just use simple files, you get what's called data redundancy. That's just storing the exact same information in a bunch of different places. And that, of course, leads to data inconsistency, which is when all those copies no longer match up. Trying to get a specific report becomes this huge manual chore, and all your data ends up isolated in different silos, making it pretty much impossible to see the whole picture. This right here, this just illustrates the problem so well. I mean, if you have two different versions of the truth, you have no truth at all, right? This kind of confusion isn't just a little annoying. For a business, it can be an absolute disaster. So how on earth did we fix this mess?
Well, we needed a hero. We needed a system that could come in and just impose order on all that chaos. And that hero is the Database Management System, or as you'll hear it, DBMS. But to really get what a DBMS does, we got to quickly define its building blocks.
So first up, you've just got data. Think of this as all the raw, unprocessed facts and figures. It's like having an entire textbook, every single word just sitting there. All the information is present, but it's not organized or useful for any specific purpose yet. Okay, next, a database takes all that raw data and it gives it some structure. It organizes everything into what we call an interrelated collection. So instead of just a random pile of facts about, say, students, their attendance, their grades, you now have a system where you can actually see how it all connects. And finally, we get to the DBMS itself. This is the really powerful software that acts as the manager, kind of like a gatekeeper for the whole database. It's the tool that lets us store information, change it, pull it out, and do it all efficiently and, more importantly, safely. It's really the brains of the entire operation. Now think about it. For us to trust a DBMS with something as critical as our bank accounts, it has to make some really serious promises. It has to follow the super strict code of honor for every single operation, or what's known in the biz as a transaction. And this code of honor, it's known as the acid test. It's basically a set of 4 guarantees that every single database transaction has to pass to make sure the data stays correct and reliable no matter what happens. These 4 letters, ACID, they stand for atomicity, consistency, isolation, and durability. Let's break down what each of these sacred vows actually means, shall we?
First up is atomicity. This is the all-or-nothing rule. It's non-negotiable. Think of a bank transfer. It has to be atomic. The money has to leave one account and arrive in the other. The entire transaction either completes successfully or none of it does. Poof. It rolls back like it never happened. This way, no money ever just vanishes into thin air. Next, we've got consistency. This one's all about making sure that any transaction takes the database from one valid state to another. Put simply, it just enforces the rules. If there's a rule that says an account balance can't go below 0, any transaction that tries to do that will just get rejected, flat out. This keeps all the data logical and correct. Then there's isolation. This one is so cool. Even with thousands of people booking tickets at the exact same time, your transaction is completely isolated from all the others. It's like you're in your own little bubble. This prevents other operations from interfering with yours and totally messing up the result.
And finally, we have durability. This is the promise that once a transaction is successfully saved, it's permanent. It's there to stay. It'll survive a power outage, a server crash, you name it. This is exactly why you can trust that your bank balance is safe. That data is durable. So these acid properties, they're fantastic, right? But trying to apply them when you have millions of users all hitting the same data at the same time, what we call concurrency,
Well, that creates some really, really tricky situations that the DBMS has to be smart enough to solve.
This slide shows the classic lost update problem. Just look at this. Imagine two people both see that there are 10 seats available at the same time. So you go ahead and buy one, and your transaction updates the count to 9. But the other person's transaction, which also started by seeing 10, does the exact same thing. It also updates the count to 9. So what's the result? 2 seats were sold, but the database only recorded 1 sale. An entire update just got lost.
And that's just one example. There are all kinds of other nightmare scenarios, like dirty reads, where you might read data that hasn't even been permanently saved yet, or unrepeatable reads, where you read the same piece of data twice in one transaction and somehow get different results. A good DBS is designed to prevent all of these crazy things from happening. So why does all this technical stuff actually matter to you? Because these principles, they're not just some abstract concepts for computer science class. They are the invisible bedrock that supports almost every single major digital thing you do every day. Every time you check your bank balance, book a flight, see that only 2 left in stock message on Amazon, or even just like a photo on social media, you are relying on a database in the background, diligently enforcing these rules to prevent total chaos.
So, if there's one thing to take away from all this, it's this. These systems are not just passive storage boxes. They are active guardians. With every single click, every tap, every transaction you make, they are working tirelessly to protect the integrity and the consistency of the data that basically runs our world.
The ACID rules give us incredible safety, but they can sometimes be a little slow. So that leaves us with a really fascinating question. What happens out there in the world of big data and massive, massive scale, where some systems actually choose to strategically bend or even break these rules to get more speed? What does that world look like?